I'm really pleased to be here. It's a great location, great office. So this talk is titled "The Road to Akka Cluster," and it's going to be sort of an unusual talk, I guess, for a Scala meetup. It's not really going to be that much about Scala. I mean, Akka is part of the Scala distribution, right? So it's in a way indirectly related, but it's not going to be really about how to use Akka either. So this talk sort of assumes that you know what Akka is all about. Instead, I'm going to try to give you sort of a walkthrough about the history of distributed systems and sort of what have inspired Akka, and especially this Akka cluster. We're really standing on the shoulders of giants here. And we owe a lot to all the great papers and all the great research and all the great products that have been done the last like 20, 30 years. And so I'm planning sort of walking through some of the highlights for me, and then also that's sort of the first half or perhaps 2/3. And then talk about how we apply this in Akka, and actually how Akka cluster is actually implemented, how it's working under the hood. And if you have no clue about Akka, sorry. I mean, hopefully this can be interesting anyway. And if you never used Akka cluster, you at least know, I mean, how it's working underneath, and you can go home and try it out. So that's essentially the idea of this talk. So starting, what is a distributed system, and why would you need one? The answer is, one of the answers is that, why would you need one? You're already using one. The distributed computing is really the new normal. You have a distributed system, you're using a distributed system, I guaranteed you, even if you're not aware of it sometimes. Mobile is definitely a distributed system. Especially since clients can go offline and the clients do updates, and when they come back online, you need to sync things back. All the challenges of distributed computing comes back, and there's a lot of things that we can learn from history that helps us deal with that problem. Same thing, almost all SQL, both SQL and NoSQL databases have replication, that both like offline replication and like async and synchronous replication and so on, and knowing what is what and how things actually work and how you can tune it can be really the matter of, the difference between success and failure. And REST, is also a distributed system. All cloud services that we use, and we actually usually deploy now on Amazon. All these virtualized environments actually encourages us to use distributed systems because it's a lot cheaper to buy just an account or at Amazon, or if you run it yourself, to run commodity hardware, really inexpensive boxes, but many of them, instead of buying these really beefy boxes, right, 48 cores or whatever it is. So scaling out is the trend. Scaling out is really more cost efficient, and that implies a distributed system. Okay, so what is the essence of a distributed system? If we try to sort of nail it down, yeah, it's been said that it's tried to overcome two things: that information travels at the speed of light. That means that we have latency now in communication that it becomes very apparent. That we wasn't when we run just in process, just regular method dispatch. It's not that clear, but latency becomes a big factor in how we have to design our systems today. And also, the second thing that, what is this sound? Okay, some soundtrack. So that is that independent things can fail independently, and a distributed system is really. I need to stand here, I guess. Okay, that's the clue. Independent things fail independently, and in a distributed system, things are really fully independent. You have the network in between, and this means that things can actually fail without you immediately noticing that. And as we all know, the network is inherently unreliable. Messages can easily get dropped, and so on. This makes it a lot harder. But why would we need a distributed system? We need it for scalability reasons. When we sort of outgrow the resources on a single node, or then we need to go, as I said, cross nodes. When we need to provide availability, you can't possibly provide full resilience and availability using a single machine, because the clean lady might just unplug it, right? That's actually happened. Roland told me a story, but where that actually happened. They actually had redundancy at this lab that he was working as a physicist. But the cleaning lady actually pulled out both plugs from both of their machines, right? So, I mean, shit happens, right? And we better have a good way of dealing with that. So availability, providing that resilience if one node fails, you need to scale out. You need to be able to have sort of some sort of distributed system. And rich stateful clients, as I've already said, also, some people don't think about it, but all the sort of classic problems of state management becomes really, really apparent when you're working with stateful clients and you have the network, because they can get disconnected. And how do you then merge things back, and how do you continue from there? So what's the problem? Yeah, the problem is that it's really, really hard. It's still hard. And we've been trying to learn these things for 30 years, and it's still very, very hard. One thing that makes it so hard is that you can't really tell the difference between a slow node that's just doing GC or is very under heavy load, or that is dead, that is down, and will never come back again. And since you can't tell this difference, you need to have different strategies to work with this. We're going to look at some of them later. And as I said earlier, the network is inherently unreliable. Kyle Kingsbury and Peter Bayliss, they just recently wrote this great paper called "The Network is Reliable," and I really encourage you to read that. It gives you sort of about 30 different case studies. 30, I'm just making that up. 20, 40, I don't remember. It was a long list of really sort of enlightening case studies of things that can go wrong as soon as you have a network. You better be prepared for the worst, really. And most, I guess, probably have heard about the sort of the 8 fallacies of distributed computing by Peter Deutsch. The network is reliable is the first fallacy. There's no such thing. Latency is 0, bandwidth is infinite, the network is secure, topology doesn't change, there's one administrator. I mean, human error you should not underestimate, right? The cleaning lady or someone that you just almost completely out of the picture when you design the system. Transport cost is 0. The network is homogeneous. We should really put this up on the wall and sort of internalize these things, I think. So it is very, very hard, and we need to have good strategies to deal with this. I have my own graveyard of the distributed system that I visit occasionally, right? When I want to, I don't really know what I'm doing there, but anyway, it gives me peace somehow to know that I'm past this. Guaranteed delivery just doesn't work. There's no such thing as guaranteed delivery, at least not generically. You can provide that within a certain boundary, within certain well-defined context, but not generically. Synchronous RPC is another thing that I don't think just doesn't work. Steve Winoski wrote this great paper called Convenience over Correctness that I really encourage you to read, where it talks about this, that emulating synchronous method dispatch on the cluster is just doomed to fail. And distributed objects, Martin Fowler said it well when he said, they suck like an inverted hurricane. It's actually an actual quote from one of his books. And I have to agree. I mean, in general, shared distributed mutable state is bad. I mean, we all know that hopefully that shared mutable state is bad if you run it on a single machine. It just gets worse when you try to do it on the cluster. And distributed transaction, XA. I mean, I've bled a lot. Okay, general strategies. I think you should sort of adopt is divide and conquer. Try to decompose the problem, partition for scale, and replicate for resilience. And other general strategies, I mean, this requires you to sort of have some solid principles. And these principles are some of the ones that we try to sort of teach and make people understand when we talk about reactive systems. Systems that are scalable, elastic, there are message-driven, that are resilient and can really be fully responsive, even when things fail and when things when you have like peaks in load, unpredictable, and so on. So the essence of it is that if you rely on loose coupling, local state, keep state that belongs together, local, and have isolation, and rely on asynchronous computation, right? Message passing across these, so you have an asynchronous boundary to get this loose coupling. This gives you location transparency. That means that you have this, that your component can actually run whenever. You have these references to your components, and you don't need to sort of care where they live, and you sort of go well beyond these all the problems with RPC if you fully rely on asynchronous message passing instead of having this classic blocking RPC. So how can we make all this happen? Yeah, let's look at some of the research that's been done the last 30 years or more. Let's start by something called the impossibility theorems. There are a bunch, but there are a couple that I think are more important than others. Impossibility theorems it sort of gives you a negative result. You can say it shows what is not possible, and by showing what is not possible, it gives you a sort of glimpse of what is possible. So it can point you in the right direction, so to speak. One classic one is called impossibility of distributed consensus with one faulty process, and that is sometimes called the FLP paper through like the names of the three authors: Fisher, Lynch, that's Nancy Lynch, Patterson. I don't remember the first names of these other guys. It was from 1985, and it can be sort of summarized in that the FLP paper results shows that in an asynchronous setting where there's only one processor that might crash, there's no distributed algorithm that solves the consensus problem. And this might shows pretty harsh, but in the FLP paper they sort of end by saying that these results do not show that such problems, meaning consensus, cannot be solved in practice, but that they point for the need for more refined models of distributed computing, and a lot of these models have then evolved ever since. And another very interesting sort of negative result, you can say, like impossibility theorem, is a CAP theorem. Most people here have probably heard about that, even if you hadn't heard about the FLP paper. And that was a conjecture, I think, initially proposed at a keynote by Eric Brewer in 2000. But it was later proven by Nancy Lynch and Gilbert in 2002, a couple of years later. This is the name of the paper, by the way. But essentially, it proves that linearizability, that's very close just to serializability. You know serializability from database, right? Whenever with this like total ordering, and basically you like shoehorn everything through a single writer, essentially, at least conceptually. That's not possible in a distributed environment. And it introduces this idea with you have CAP stands for consistency, availability, and partition tolerance. So, and out of these three, you can never have all three. You can just have two at a given point in time. So and if you have a distributed system, then you have P. P means basically that there can be a network split. That means that you only have one choice, and that is choosing between consistency and availability. There's no way around that. And this have been a very highly influential paper. I'm going to talk more about that, everything that's sort of inspired later. But first, then, what is linearizability? What does it mean? Since it proves that it's not possible in a distributed system, at least not in a fully available scenario. So Harley Wing in 1991 defined it as under linearizable consistency, all operations appear to have executed atomically in order that is consistent with the global real-time ordering of operations. Yeah, so what does this really mean then? Less formally, you can say that a read will return the last completed write, regardless of where it's made. If you have a cluster of 1,000 nodes, and the reads and writes happens all the time, any read will return the last completed write regardless of where it happened. This is a very strong guarantee. It's extremely costly. And we can't possibly need that for everything we do. So the question is when and how. And if we, so as I said, CAP was sort of extremely influential, but when looking back at it a few years back, now it's like 14 years, it actually shows that it had pretty narrow scope, I think. Peter Bayliss in this HAT paper, I'm going to come back to that later, highly available transaction paper, said that CAP has led to confusions and misunderstanding regarding replica consistency, transaction isolation, and high availability. And the thing is that the essence is that linearizability is a very strong guarantee, and it's not very often required, actually. Sometimes it is. But it's the same problem, like we have an Oracle database in our infrastructure, we just shoehorn everything down there. I mean, it's convenient, right? And you can all use all the tools for data mining or whatever, but it just won't scale, period. Oracle Rack might help you, but I mean, then you like have to sleep out on the street instead. The second thing is that it ignores latency almost completely. And latency has a very practical meaning. You know, we started by defining a distributed system as sort of a cap on the speed of light has really big impact. Latency matters, and partitions are actually pretty rare, even though the P stands for partition tolerance. But partitions are rare. So why then do we need to sacrifice consistency or availability all the time? It doesn't make any sense. Instead, I think we need more fine-grained models for dealing with these things. Ideally adaptive models that sort of give up on certain guarantee when it just has to, not all the time, not just black and white. And most NoSQL databases that came out of this movement of eventual consistencies, they were either like black and white initially, and this starting to change, I think. Even Eric Brewer wrote this great paper, or article, more an article than a paper. It was written on InfoQ, I think. CAP 12 years later, where he actually argues for most of these things. So that was impossibility theorems. Another very important thing, I think, that in order to work with distributed systems, we need a way to work with time. Time needs to be first class in our programming model. And you can't just hand wave that. And thanks to Leslie Lamport, we have pretty good ways of dealing with time now. In '78, he wrote this extremely influential paper. It's probably the most quoted paper in computer science history. Was it Time and Ordering in Distributed Systems, something like that. I always forget. It's a pretty long title. Where he talks about logical clocks and causal consistency. They are now usually named sort of Lamport clocks, and it's sort of a virtual clock or sort of a, what do you say, sort of an abstract concept of clock, basically just a counter. So when a process does work that is important, then it increments the counter. And when a process then sends a message, he includes the counter. Okay. So and when the receiver receives the message, it takes the counter and it merges it with its own counter. This gives you causal consistency, and you can make sense out of ordering in a distributed system. This was extended by Colin Fidge in 1988, and actually he wrote a paper concurrently with some other guy that nobody remembers the name of, at least I don't. So they both sort of discovered vector clocks then, which is an extension of Lamport clocks. And in vector clocks, each node, a node doesn't have to be a physical node. It can be a user. It can be something that's sort of, yeah, has a role of a node that that need full consistency not full consistency, but that needs to play a part in causal consistency in a distributed system. Each one of these owns and increments its own vector clock. So in a way, you have like a map of nodes to Lamport clocks. Okay. And the way it works is that each one of these, they always keep the full history inside the vector clock. So they are fully self-contained. And it has sort of a monotonic merge function. If you heard about CRDTs, and we'll talk a little bit about that later, they're very, I mean, vector clocks is actually a CRDT, where you have a monotonic merge function that would always, successfully merge. And that is an extremely useful tool. We see out there using, I mean, in most sort of eventually consistent databases today. We use them in Akka, as we'll talk about later. So now we have a good way of working with time, and a way better than I think some databases use last write wins or so. That can really lead to data loss. Vector clocks has its own set of problems, like how do you prune the history, for example? If history grows forever, you might need a way to actually prune that history, because the data that in the vector clock you need to send around just grows, right? But there are good research of that, like dotted version vectors, for example, helps you with that, and so on. So I'm optimistic. Failure detection is another thing, and as I said, there's really no way of knowing if a node is down, I mean dead, or if it's just doing GC, if it's Java, or if it's just a temporary network split somehow. So failure detector is more of like sort of like an art or like a black science or whatever you want to call it. There's no such thing as I know for sure. You can only do guesses. So a good failure detector is really good at guessing if sort of the likelihood that the node is down, basically. So in order to understand failure detection, we can first like look at a formal model to categorize failure detection. So the first thing is strong completeness. Strong completeness means that every crash process is eventually suspected by every correct process. This is as good as it gets. Okay. Weak completeness is that every crash process eventually suspected by some correct process. This might be okay, as long as someone like detects it and can start like telling others about it. Strong accuracy means that no correct process is suspected ever. Meaning, if you have done nothing wrong, you shouldn't be like busted for it, right? And have to like explain that you haven't done anything. So this basically means that there are no false positives. Weak accuracy is that some correct process is never suspected. And that's basically can be translated like some false positives. So in an ideal world, you have strong completeness and strong accuracy, but you perhaps don't need that. Everything has a price, especially in a distributed environment. Things are very costly. So yeah, it's not always an easy choice to make. One interesting paper is a paper about the Accrual failure detector by, I think it's a Japanese guy, Hayashibara. Sorry if you're Japanese, no offense. This is actually the one that we're using in Akka, and we'll look into that and some problems with it as well later on. So the Accrual failure detector actually does what I guess what you can guess, right? It sort of gathers statistics and keeps statistics around from heartbeats. And another nice thing is that it decouples monitoring from the interpretation of that data. And what it does, it calculates the likelihood that a process is down. So you don't get yes or no, you get something called a phi value back. That sort of shows you how likely it is that a process is down. And this gives you more freedom to use that. I mean, it might be that all of them are suspected, but then you can sort of, or like half of them are suspected to some degree, but then you can sort of continue to send messages to the one with the high likelihood, or the low likelihood of being down, while ignoring the ones with high likelihood and so on. As I said, there's no such thing as black and white. You never really know. So you just need a failure detector that is good at making guesses out of like data, basically, not just flipping coins, of course. So when you plot out one of these, it usually have this sort of classic J curve. And yeah, here's the formula, by the way, if you're interested. I can share the slides later. It's also, I have a lot of speaker notes as well with sort of links to all the papers and everything. And there's like 10 pages of references at the end if you're really into reading up on all this, which you should be, actually. It's your future. Another very interesting one is the SWIM failure detector. And it also has some pretty nice properties. It was one of the first ones that actually separated heartbeats from cluster dissemination because that means that I mean a lot of the early failure detectors sort of merge like the gossiping of state with the heartbeat. That sounds like a good idea perhaps, because if you're communicating with with other processes every second or whatever, sending out state, why not like count that as a heartbeat? But then it gives you less freedom to configure these independently of each other, and sometimes you might want to like send heartbeats more often than you actually want to do state replication. And you don't want to do state replication more often than you have to, because that usually has way more state that you need to send around, while heartbeats can be extremely small and very, very efficient. That's why it's good to separate them, I think. It also introduces something like a concept of a quarantine, where even if you suspect that the process is most likely down, you just don't mark it as down. You actually put it in quarantine and let some time pass, and while he has the opportunity or the possibility of getting out of quarantine, if you were wrong, which actually very often happens. But if the time passes, he's doomed as faulty and he can't get back again. Another interesting, and probably the most interesting contribution in my view from this paper, was delegated heartbeat, and that's a very sort of cool way of sort of getting around network splits. So the way it works is, if I would try to explain it, is if you have two processes like Alice and Bob, if you want to use this as a classic sort of names in computer science. So Bob sends a ping to Alice to see, are you up? If Alice responds, things fine, she's up, okay? If she doesn't respond within a certain timeout, instead of marking Alice as down, what Bob does is that it sends a message to like 5 or 3 or whatever random nodes in the cluster. One of them might be Bob, for example, and then Bill. Sorry, it's either A, B, C, I guess, but anyway. Okay, so then he sends a hint to Bob, say, could you go check Alice out? And so Bill then goes and sends a message to Alice and a whole bunch of other friends. And if one of them is able to reach Alice, then Alice is apparently healthy. It was just a network split between you and Alice, between Bob and Alice, right? And so there's a way around the network split, and things might be fine. This sort of network connection might heal eventually. But if all these sort of candidates that you ask to check for Alice returns with a timeout, then Alice is apparently down and you can mark her as down. So I think this is something that we've talked about at Akka, but we haven't done it yet. It's an interesting optimization, or it's an interesting way of taking the accuracy of the model even further, I'd say. Strong consistency. Yeah, that's basically about linearizability, and that's sometimes needed, but it has a very high cost, I think. And where there's been some pretty interesting sort of papers lately about that actually, I said in the beginning, it was even part of my graveyard, right? The XA transactions are doomed to fail. Distributed transactions are actually on its way back, but in a different form. And one of the great papers there is by Peter Bayliss. It's a very recent paper. He talks about highly available transactions, and he talks about hat then instead of cap. Yeah, it's sort of cute in a way. So, and sort of the summary of that paper, and what I think is interesting is that he argues that most SQL databases, they do not actually provide serializability. We might think they do, right? We learned when we talked about relational algebra and stuff and in computer science course at university, that is sort of the optimal way. They actually don't do that. They have weaker guarantees, and that's for performance reasons. And the interesting is that some of these weaker transaction guarantees are actually possible to implement in a fully highly available manner on a cluster, which I think is really fascinating. And the question is then that they ask is, what transaction semantics can be provided with high availability? And they this is from the paper here actually where they list the different guarantees that gives. For example, in Oracle, it doesn't give you serializability. The best you can get is read committed. And the interesting thing is that when you start looking at it, read committed is actually possible to implement in a fully highly available fashion. So you can actually give the same guarantees as Oracle and scale out in being fully highly available. Some of the ones that are unavailable is like serializable, for example. Because if serializable was possible to be highly available, then the CAP theorem would be wrong, right? So it's an interesting paper to read. Other research papers around this is another one by Peter Bailey called bolt-on consistency. It's one called Calvin that I found intriguing as well. Spanner, you probably heard of. Google, they rely on atomic clocks. I think they're, yeah. I won't go into details too much about this. Just go on instead. Consensus protocols is also something important and that most people know about. And most people have heard about Paxos, for example. But before we do that, let's look at some properties that these consensus protocols need to have. So if we have then first two events for this little model, that we have request and we have decide for a specific value. Then termination means that every process eventually decides on value v. Okay? Validity means that every process decides v. Then if a process decides v, then v was actually proposed by some process. It was just not randomly made up. That's a pretty interesting property. Integrity means that no process decides twice. That would be unfair. And agreement means that no two correct processes decide differently. So you have then full consistency. Okay? And some of the consensus algorithms that implement this is Paxos, for example. That was probably the first one by Leslie Lamport. By the way, Leslie Lamport is giving the closing keynote at React in San Francisco here. I was really excited to get him on board on doing that. ZAB is another one. That's the Zookeeper Atomic Broadcast Protocol. That was another one. And a very sort of one that came out fairly recent that's been immensely popular is Raft. I don't know if you've heard about Raft. The interesting thing about Raft is that they set out to come up with a protocol that actually was understandable. Paxos is extremely hard to understand. I mean, there's for a reason that Les Lamport, I think, wrote 7 papers trying to explain Paxos, right? One actually named like Paxos Made Simple, and still no one understood it. And what's really hard with Paxos is that it's almost impossible to implement it by the spec in the real world. You always have to diverge slightly from the spec, and guess what? Then you have a fully unproven model that you have to prove yourself. Raft, what these guys have said, they set out to create a simple model, simple to understand, but it actually turns out to perform very, very well. So I encourage you to look at Raft. There are implementations in most languages nowadays, and Raft and consensus. All these consensus protocols they implement CMP. That means they are not highly available. If one node is gone, then you can't have consistency. There's no way to get agreement then. Another interesting thing that's not really research, but that I think is important to mention is sort of the the popularity of event logging and how to design your system as especially event-driven system, a message passing system using an event-driven or you're using an event log, and the first thing here is that it favors immutability. All events should be immutable, and you should really have a fully share nothing architecture. And I really think that is the true path towards scalability. And we should think in facts. Pat Helen, giving the second keynote at React, I'm really happy about it. He's one of my role models. I mean, all his work with Jim Gray in the 80s and stuff. So he said that the database is a cache of the subset of the log, which is pretty interesting. You know, Oracle already has event logging and transaction logging under the hood, right? It's just they don't expose that. They just expose the latest snapshot of that log to you. What if you need all the stuff down there, right? Tough luck. You need to do it yourself. And that's what's really starting to happen now. I think there's no reason to not keep state around forever. It used to be when disk was really, really expensive. Today it's so cheap, so let's just keep it around. And in-place updates just need to die, I think. There's really no sane reason to keep on doing that. So keep everything in logs. Never delete data. Knowledge just grows. Why delete knowledge, right? Important things that you might need later. And it's also very, very efficient. If you have, you can apply the single writer principle, just writing very, very fast to the log, and minimize contention. And yeah, we don't need to go into this. So another interesting thing is then eventual consistency. We talked about strong consistency. Eventual consistency, that basically means that you don't have consistency at the moment when you might ask for it, but it guarantees that eventually the system will sort of coordinate in a way that you get sort of stable values. You get agreement. And one of the sort of most important papers for this was a Dynamo paper. It was extremely influential, and it popularized mainly the first three things here. It popularized eventual consistency. It really set off to create this sort of trend of NoSQL databases that are eventually consistent. And it also popularized epidemic gossip and consistent hashing, both of we will look into later, and that Akka has adopted. Some other interesting strategies like hinted handoff, for example, sending data. If the node that you need to replicate to is not available, you can send it somewhere else with a hint. Whenever that guy is up, send the data to him, and things like that. Read repair and so on. You should read up on that yourself if you're interested. Consistent hashing is a very nifty sort of strategy that gives you a very nice way to support full elasticity, meaning that nodes can come and go. So you can really live up to the promise of cloud computing without too much of a hassle. It basically gives you a way of, if you lay out all your nodes in a node ring, then consistent hashing means that you consistently hash all the buckets, and you have a very sort of a nice way of doing like partitioning and replication, and add nodes in this ring. This ring can expand and shrink without you having to sort of do much work. One question though is how eventual is eventual consistency, and how consistent is eventual consistency. I said there's nothing black and white. You can't say in 1 second my system is fully consistent. Eventually sort of a bit fuzzy, right? So how can you make sense of this? And that's a hard question to answer. But Peter Bailey's group at Berkeley, they've also done some pretty interesting work here that I think is worth looking into. They call it probabilistic bounded staleness, PBS. And it gives you sort of a model. They even have actually a live demo on their website where you can start typing things in. It really gives you a model to see how eventual and how consistent it is over time. Here you can see like how long it takes until here's like time after commit, how long it actually takes until the system is fully eventually consistent using different sort of thresholds. So I won't go into that paper. I'm just giving you a hint that it's worth checking out and give you good models for actually making sure that you are within the SLAs. Because if you start using eventual consistency, it might be that you screw up and the latency is too high until you actually have full consistency. If you use the right model and know what you're doing, you can avoid that. Lastly, I want to talk about, before we get into Akka, I want to talk about another trend that is starting to happen a lot. That is called disorderly programming. They also call it ACID 2.0, sort of nifty if you look at the acronym what they mean. A stands for associative. That basically means that the system or the coordination is batch insensitive, meaning the grouping doesn't matter. It's commutative. Everyone knows what commutative means. That means basically the ordering doesn't matter. And that is idempotent. That's the I. So A, C, I. And D stands for, I don't know, distributed perhaps. is sort of fuzzy. Idempotent means that duplication does not matter. And some of these are eventually consistent, by the way. And some of the sort of practical applications to implement these ideas are CRDTs. Have you heard about CRDTs? Okay, yeah, not that many. You should actually look into that. They are an extremely useful tool, I think, in distributed systems. If you can model your data as CRDTs, you're basically fine. Let's say you can go home. No, it's not that really that. But still, you can get pretty far. So CRDTs basically stands for convergent replicated data types or commutative replicated data types. Some also say conflict-free replicated data types. They have lots of names. But the interesting thing is that most. So long story short, most sort of eventually consistent databases, they basically just implement one data structure. That's a register, key value. You know, Voldemort and the old Dynamo and React actually have links, but most of them actually implement some sort of key value store. CRDTs actually gives you a way of modeling much richer data structures than registers. Counters, sets, maps, even graphs with the same properties with that sort of Dynamo and React and Voldemort and these gives you. Okay, so the question is, if you can model your data as a CRDT, which it has some sort of properties that you need to hold. One is that they need to have a monotonically increasing merge function. That in math, see that they need to be a joint semi-lattice. Yeah, I won't go into detail about that. But the paper is actually very approachable. I think it's very easy to understand, and it implements sort of availability and partition tolerance. It sacrifices C. But the interesting thing is that these data types now you can just update and throw out there, and someone else can update it. And as long as they reach all replicas, they will eventually be consistent. They will eventually converge. And this is that's sort of an amazing property. The thing is that the caveat is that not all the problems can be modeled using CRDTs, but the ones that can, it simplifies things a lot. And there are two types of CRDTs. There are the state-based, the CVRDTs. They are convergent. They are basically have the same properties and problems like vector clocks. They keep all the history around. They are fully self-contained, and that's a good thing, right? Because that means that you can send them off even to mobile devices, and they can do all kinds of updates. And when the network comes back, they will just automatically converge, and things will be consistent. It's a very nice model. But you have potential problems with sort of the history grows over time. And then you have also these commutative ops-based, so to speak. They require a fully reliable broadcast channel. And there you don't send the state around, then you send the behavior around and have that being updated on all nodes. Calm theorem, we can skip. It's very interesting, but I'm running out of time a little bit. Epidemic Gossip, as I said, was really popularized by Dynamo, and I say it's really popularized by Cord. Cord is not. It was sort of initiated by Cord. So Cord made it popular in the research community, I'd say. Dynamo brought it to the masses. So, and it's basically gives you a way of when you lay out all nodes in a node ring. It really does sort of epidemic gossiping in the same sense that diseases spread, like biological. It's fully sort of probabilistic, and it just happens randomly. But it has a lot of nice properties. So it usually converges very quickly and so on. And it also implements then A and P. Everything is of course then fully eventually consistent. So the benefits, I think, about epidemic gossip and the reason why we have fully adopted in Akka is that there's no centralized coordinator. All nodes are equal. There's not even any specific roles. So there's no single point of failure. It's extremely elastic. Nodes can just come and go as they want, and therefore very, very scalable. You can easily have clusters of thousands of nodes and so on. And so this brings me to Akka. It was a long journey, right? I'm exhausted. Are you exhausted? Okay, but now let's just take a look at how Akka is using all of this, or what we use, and perhaps also talk some about why we don't use certain things. So cluster membership in Akka. You know, Akka cluster has cluster membership. You can just spin up nodes. They will automatically be detected and join the cluster, and they can come and go and so on. We're heavily influenced by Dynamo, so we use a masterless or decentralized peer-to-peer model. Using epidemic gossiping, we actually do the same thing. We lay out all the nodes in a node ring, and we do sort of semi-random gossiping between them. We use vector clocks. That's our way of sort of keeping track of time for causal consistency. It's extremely important. We can't possibly make sense of anything without vector clocks. And it's actually both extremely scalable. I mean, we can easily run unoptimized. We were running 2,400 nodes on Google Compute Engine, and even more interestingly, we were able to spin up 1,000 nodes in less than 4 minutes, and that includes actually all the virtual instances inside the Google Compute Engine. And so this is the time until we reach a fully sort of connected, coordinated cluster. So yeah, this is a node lifecycle. I don't know if it's really that interesting, but we have a bunch of stages. The interesting thing I can say though is that the node lifecycle and the data structure we use to represent this is actually a CRDT, but we never thought of that until we started reading up on CRDTs. We sort of, in a way, sort of naturally evolved towards a full CRDT by just sort of trying to make sense of something that could work in a distributed environment. So we essentially. So the gossip that we then send around when we do epidemic gossiping looks like this. So we have a set of members. All the members. This is basically the node ring. That's why it's a sorted set. We have something called the scene set, and that's extremely important. I'll talk more about that in a second. Then we also have a list of all the nodes that are reachable, or even more important, unreachable. These are the nodes that are marked unreachable by the failure detector. And then we have this whole data structure versioned. I didn't say that, but one very nice property of a CRDT is that the CRDT is composable. So a CRDT can be composed out of CRDTs. You can make big data structures out of small ones. And we make use of this here. I mean, vector clock is a CRDT that is composed with this larger sort of data structure. Yeah. So a very important concept in Akka cluster internally is cluster convergence, and what that means, basically that. So when we start gossiping around, when a node has seen the state and seen that it has sort of the same vector clock, then it puts himself in the scene set, so to mark that I have actually seen this value. If the sort of version that you get is lower, then it actually replicates back the newer one. If the one you get is newer, then it does a merge and updates himself. So this is the way so the cluster very quickly can converge. And this is how we can keep track of when we reach consistency, because we reach consistency when all nodes are in the scene table or in the scene set, meaning that then we know that everyone has seen this version because it's version. Are you with me? As soon as someone has not seen it, it will increment. As soon as a change happens, a node comes, a node leaves, then a new set will be put into the gossip, and the version will be incremented. And this means that we have full inconsistency again, and everyone needs to start sort of marking that they've seen this value. This unreachable thing is also very, very important, because as soon as there's one single node in this list with unreachable nodes, that means that we can't have convergence any longer. Because in that node, because one of the nodes is actually down. We'll talk more about that later and why that is really, really important. One optimization that we do is what we call biased gossip. I haven't really seen that sort of name used anywhere, but it's a way to have the whole cluster converge more quickly, basically. So we have 80% bias to nodes that are not in the scene table. So we actually check the scene table, and with 80% chance we actually gossip to the ones that are not there to have it converge faster. That said, we initially did that for like all clusters, but it turned out like empirical evidence showed that beyond 400 nodes, then it actually was not such a good thing, because if you have like sort of the nodes that are in these 20% will easily get sort of flooded with messages from all this. So when we start reaching 400, we actually slowly start sort of decreasing this percentage. And another interesting sort of optimization we do is push-pull. That means that if we know that we have cluster convergence, there's really no reason to send all this state around. Then we just send the version around, which is extremely little data. And in the default case, that's usually, the default case is usually that it is convergent. That the cluster is convergent. It's not convergent just when nodes leave and go or become unreachable. So this means that in the default case, we actually don't send much data around at all. But as soon as either a node, one of the nodes detects that the failure detector has marked a node unreachable, so the unreachable sort of list is not empty any longer, or that sort of the scene table is not complete, so to speak, then it goes back to regular gossiping again until we reach convergence. We also have a concept of a leader. We do not do leader election. Fully consistent leader election, like a la Paxos or Raft or so. And instead, the thing is that instead we rely on the node ring. What we do is that we hash the node ring using sort of a deterministic algorithm. So it's always the same order for every single node. They can't end up with different sort of orderings in this. And then we just pick the first guy to say this guy is the leader. It really doesn't matter which one it is, because it's a role that we use. The leader has duties, but it's not anything that requires much load at all. So that's a pretty nifty way of getting away with having a leader in the cluster without actually doing any extra work. So, and the leader can of course change after cluster convergence. If the leader goes down and not coming back again, there will naturally be another guy that's first in this list, and he will be the leader and take over the leader's duties. The leader's duties is basically to manage when nodes join and leave the cluster, moving him from different stages. If you remember this state diagram I showed some slides ago, actually make sure that it moves them, because it needs to just be one that does that. So as soon as it's moved one from joining to actually being a fully fledged member in the cluster, it adds that in the gossip information and starts gossiping it around until we have full convergence. Then everyone knows that the new node is up and healthy, and they can start using him. So that's basically how it works. Failure detection, as I said, is extremely important as well. And a naive one would just sort of do heartbeat to all of the nodes. We picked a configurable value of 5 that we start heartbeating to 5 different nodes. And we do that in a sort of conversational way. We had thought out a very clever algorithm where we actually can only send one heartbeat, and we can still sort of understand through some sort of, without getting into all details about the actual protocol, but we sort of figure out in a sound way. I mean, if it was down or not, but we changed that to like a simple request reply, basically ping Akka, are you up? Yes, I'm up. Because it became unmaintainable in the long run. And we use failure detection not just for cluster membership, but we also plug that in to do really reliable remote death watch and remote supervision. I don't know if you used the sort of reliability or the failure model in Akka, in the actor model, but we have something called death watch where you can actually watch how an actor is doing, and we have supervision that's like the parent-child relationship where you manage the failure and the health of your child. That used to not work across the cluster very well. Just because we were lacking a reliable failure detector. So once we had that in place, that just works. You can just link to a remote actor, and it will very reliably work. Am I running out of time? Okay. 5 minutes? Absolutely, no problem. So we are actually using an accrual failure detector, but the interesting thing is that I don't know if probably because we run on Java where we have GC and so on, it actually doesn't help much in practice, because usually GC take precedence over network hiccups. So instead, I mean, in an ideal case, we would see something like this, like as an optimal configuration for our failure detector. But instead, usually it looks like this. So we added this acceptable heartbeat pause, where we were able to stretch it out just to deal with things like GC. That usually is way more common and takes way longer than like network hiccups, unless it's actually down. Of course, then it's fully flat. But so we argued if we should just remove this sort of fancy like statistical gathering or stuff, because I mean, you only start making use of that over here. Network partitions is another thing. People ask how we deal with that, and that is one of the biggest, hardest problems, right? When you start dropping messages on the floor and so on. And as I said, the failure detector, its job is to mark nodes as unreachable. So if suspicion is high enough, then it adds them to this unreachable list, okay? And as I said again, if a node is in the unreachable list, then the cluster does not have convergence, and this means that the leader can no longer perform his duties in a reliable fashion. This is what we normally call split brain. And the thing is that there is really no good automatic way out of that. Okay. You have a few options. Ideally, the member will come back from unreachable, and then we actually remove him, and things are fine. Then the cluster sort of heals itself. But you need to have a timeout on that, of course. That's basically the quarantine in the swim failure detector that I talked about. So if that is the case, if it doesn't come back, then we need to mark the node as down. If the node is marked as down, then it's out of the picture again. It can never join back. And then the cluster can continue without that node, or that set of nodes if you have a network split like in the middle. And we used to have something called out to down as the default. That means that the leader can actually take the action of saying, I mean, I will auto down you. I mean, you're not with me part of the cluster any longer. But that had some, I mean, doing too much magic can sometimes be confusing. And in large clusters, we have clients running, a few hundred nodes. It was actually hard to do that. I mean, hard to get the configuration done right, so it did that in a predictable fashion. So now we still have auto down, but we have it off. So we usually encourage you actually to have the sysadmin go in and see what really happened. Which part of the cluster should I take down, and so on. Or which node should I take down? Because if you have a network split, it might be 50-50. I mean, you might have to, like, if it's a 50-node cluster, like taking down to 25 nodes, I mean, you probably need to sort of have some human intervention or more understanding of the problem. Okay. So some potential future optimization, as I said, we're looking into vector clock pruning, delegating heartbeat a la swim, where we actually can sort of check around potential network splits. Real push-pull gossip, where we haven't really had a need for that. And what I mean by real is that where you actually do a hash of the data and only send the hashes around. Using like Merkle trees, for example, that like they do in Dynamo. We haven't really had that need because our data set is usually it's fairly small, and we use gzip on it as well. And it's a lot of redundant information. All the nodes, in the vector clocks is the same. So zipping things up is usually very efficient. So we haven't had a need for that yet. But also more out of the box auto down patterns. That's something that I would love to see people look into. I mean, from the community as well. Can we do auto down in such a reliable fashion that we can bring it back? I mean, because the more automatic things we can get, adaptiveness into the system is better, right? So finally, I just want to talk about, we have sort of built a bunch of high-level modules on top of this. So and some of the more interesting ones are that we have cluster singletons. That's sort of a pattern we built on top to ensure there's only one single actor in the whole system doing something. We have cluster routers. We take full advantage of the cluster to do routing. When new nodes come up, we just make sure that we create routees and we put them on these nodes. And same thing when nodes leave, we can migrate them and allocate them somewhere else. Cluster pub sub is a very nice like publish subscribe sort of module on top. We also have like a model for consistent hashing. That's actually a router, a clustered router that has an algorithm for consistent hashing. So we can bring that in there as well. So Akka persistence, I think I'm just gonna skip. Just some of the roadmap before I close. Akka HTTP is also distributed computing. I think REST is definitely a great way of doing distributed computing, and we're adding Akka HTTP. That's actually through Spray merger that comes in Akka 2.4. Another very interesting thing that is potentially distributed is Akka streams. Initially, we will just do like materialization of the streams like in process, but since it's all based on actors, nothing prevents us from in the future making sure the streams work across machines in a very efficient way. So you can like fan out, fan in, merging, all kinds of stuff. And that's basically that's basically what I wanted to say. Finally, I just want to say once again, please join us at ReactConf if you're interested in stuff like this. And not just distributed computing, but also, concurrency and building really resilient stuff. Join us at ReactConf. It's in San Francisco. It's actually at the Comedy Club over on. It's pretty funny, yeah. It's true. It's at the Comedy Club over on down what's it called, Columbus Avenue, I think. So check out the website and look who's speaking there. So. I'll be around afterwards for questions. I don't want to take up more of your time. I've already spoken for an hour now, so I hope this was somehow useful.
Thank you, Jonas. I think we have time for questions.
You do? Yeah. Okay, we have time for questions. At least a couple. Yeah?
Can you talk about the limitations of CRDTs?
The limitations of CRDTs, yes. Limitations of state-based CRDTs, as I said, is that it's hard to get around the problem of the growing of the history. That means that as you use the CRDTs, it will get, the state, since it's fully self-contained, that means that the state you need to replicate around will get bigger and bigger and bigger and bigger and bigger and bigger. And that might be a problem. As I said, there are interesting strategies for doing that. For vector clocks, they have sort of solved it, but for the more complex CRDTs like graphs and so, I haven't seen anything. So that is an ongoing research. For the challenges for this ops-based CMRDT, so the other call is like CVRDT. So the CMRDTs, is that it relies on a reliable broadcast channel. That means that no messages can get lost, right? Then you must ensure that every single operation, state change operation that you do, eventually reach all replicas. Else it will be inconsistent. And as we know, that can be pretty hard to do. I mean, give those guarantees. So in a way, I love the beauty of the state-based ones, but they have their problems as well. So I think we're not there yet, but there's a very interesting ongoing research around that in general. So we're just getting started.
Yeah. Do you see any hope of fixing the Java GC problem that seems to be coming up more and more?
Fixing the Java GC problems, yeah, I would love. There's a lot of things I would like to fix in Java, but that can be another talk. Yeah, I don't know what to say about that, without being very politically incorrect or without taking up another hour. So, any other questions? I can also say regarding CRDTs, they're not in Akka yet, but I started out with a project called Akka CRDT about a year ago. That was just a prototype, and Patrick Nordwall on the Akka team, he took some of those ideas and implemented them for real. There's a module now called Akka data replication, I think, that does way more than CRDTs, but it's based on CRDTs. It's a very nice module for doing like eventual consistent data replication. So please look at that if you're interested in these things and contribute. It will most likely eventually make it into Akka. Another thing I can also mention is there is an implementation in Akka of Raft. Conrad, another guy in the Akka team, did that about a year ago. I don't know if it's production quality yet, but it's pretty interesting work. That might also make it into Akka eventually, if it's picked up and used and there's a need. So there's a lot of things going on different angles. Yeah.
Time for that.
One more question, okay?
So I'm new to this CRDT thing, but just off the top of my head, I have a question. Can we, when you see a CRDT system reach the consistency status, at that point of time, can we equally say the system is also serializable in terms of the data? Can somebody prove that, or out of my instinction, I think it's true, but I'm not sure. But
yeah,
I think it should be true.
At that point, it is fully consistent. But the thing is that it doesn't necessarily need to be consistent at that specific point in time, right? Because in a fully eventual consistent, there's no like snapshot. You can just do a global snapshot and say everything is consistent at this point. Because while you're just checking that, things will happen. So it's still a causally related consistency, I'd say. But yeah, we can talk more about that offline, I guess. Okay, thank you.